Right, physics students, AS physics, projectiles. What happens if I throw one object sideways and I drop the other object, and I do this at exactly the same time? Which one will hit the ground first? The one that gets dropped straight downwards, or the one that I throw sideways? Will it take longer for the sideways one to reach the ground than the one that I just dropped straight down? Which will hit the ground first? Let's find out. That didn't quite work. You might have heard two separate bumps. It didn't do what it was supposed to do. Okay, try again. This one's going to get dropped straight down. This one's going to get thrown sideways. 3, 2, 1, go! And they hit the ground at exactly the same time. And you wonder why. And I know why, and I will tell you. Here's a cliff. Here's a person at the top of the cliff throwing something with a speed, a horizontal speed of 12 meters per second. The cliff is 108 meters high. That is one really high cliff. You do not want to fall off this cliff. But this guy is throwing bananas or something off the top of this cliff, and he's throwing them with a horizontal velocity of 12 meters per second. Now we could call that U. H equals VH equals 12 meters per second. Why am I saying U or V as if they're the same thing? Well, U means initial velocity, V means final velocity. Well, if something's thrown sideways, how much acceleration is acting on it? How much will it be accelerating? You're right, it's not accelerating. Why not? Because horizontally there's no force acting on it. But you say, but hang on, Mr. Slaney, gravity's acting on it. Yes, you're right, of course gravity's acting on it. Which direction does gravity act? Downwards. See, what I'm getting at is there are two distinct types of motion when something flies through the air and falls. We forget about friction and air resistance because they're tiny, and we just forget about them because it makes life a lot easier. But what we do have to bear in mind is that in the downwards direction, the sort of motion we're talking about is constant acceleration. In the horizontal direction, the sort of motion we're talking about is constant velocity. So, what we do is if we want to work something out, say we want to work out the distance D, I'm going to call it D, to where this object lands, here it goes, it traces a path like this, and it lands there, hits the ground, splat. You want to find out that distance D. What you do is you write data, and you write horizontal data, and you write vertical data. Please excuse my phone. You write horizontal data and you write vertical data, and you always do this every time you do a projectile problem. No matter how good you think you are at it, no matter how many times you've done it before and you think, I do not need to do this the long hard way, I do not need to write out my data. Yes, you do. Every time you do. So, horizontal data, U, little h for horizontal, is 12 meters per second. Does it speed up? No. Does it slow down? No. So V, final velocity, little h, reminding us we're talking about horizontal, is also 12 meters per second. Is it accelerating? No. Therefore, what is A? A is 0. Do we know the time taken? No, we don't. Do we know how far it travels? No, that's an unknown. S equals D equals question mark. See, normally the symbol for distance is S. Here we're calling it D, so I'm just telling you we do not know what it is. Is there anything else? No, that's our list. Let's go to the vertical data. Now, this thing is effectively, vertically speaking, it's just dropping like a stone. Maybe it is a stone. Maybe it's a banana. I don't know what it is. I don't care what it is. Vertically, U is 0. But it's moving this way at 12 meters per second. Yeah, but I don't care anymore because that's horizontal motion. Vertically, it starts by not actually moving in the vertical direction at all. V is a question mark. We do not know. Acceleration. Oh, you know that because everything that falls at the same rate on the surface of the Earth. 9.81 meters per second per second. Anything else? Oh yes, we know S. Vertical distance, 108 meters. Right, now what we do is we think, is there anything here in this list of unknowns that we can find using our SUVAT equation? Now, if you use horizontal data, you only use horizontal data. You do not touch this. If you use vertical data, you get rid of that and you just use vertical data. You cannot mix them. You cannot mix them together, otherwise you'll get everything wrong and life will be bad and you'll be miserable. And we do not want that. So, what should we try and find out? Ultimately, we want to find this distance along here, but we cannot do that straight away because horizontally you know U and V, you know acceleration is 0, you don't know time, you actually cannot figure that out. You don't have enough information. But vertically, you know U, you know A, you know S, T. You know, the time to get from there to there is the same time to get from there to there because they're both happening at the same time. So what we can do is we can say, hey, this is doable. Let's go S vertically equals UT, little vertical, plus half A T squared. I've put little V's beside all of these things to show that it's vertical data, only vertical data. So S is 108 equals 0T, which is just going to be 0, plus half times 9.81 times T squared. Therefore, 108 equals, now what is it? 4.905 T squared. Now you work that out, divide 108 by 4.905, square root the answer, and you get T equals 4.7 seconds. So that's how long it takes for this object to drop to there, or how long it takes for it to just go put 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 out in this direction until it's got to that point. It's covered that distance D, because the time is to get from there to there, which is getting from there to there and getting from there to there. This one is constant uniform motion, this one is accelerated motion. Let's just do that again. This is constant uniform motion this way, this is constant acceleration this way. Put them together, it's a parabola. Yeah. Anyway, that's the time. Now what you can do is you can figure out the distance. So I'm going to get something to rub this off. A mask, that'll do. I'm going to rub this off. We have calculated time. We've said T equals 4.7 seconds. Now, what you're going to try and do is find that distance there. So what's the formula for distance? Well, normally we say S equals U plus V over 2 times T. Now that's a pretty simple equation. That's just average speed times time. Distance equals average speed times time. Too easy, really. Therefore, let's find the distance. D, because the distance in this case is called D, equals 12 plus 12 over 2 times 4.7. Now 12 plus 12 over 2 is just 12. Go figure. 12 times 4.7 on a Monday is 56.4 meters. So we can find the distance, 56.4 meters. That's how far from the base of the cliff that banana skin is going to land if you throw it at 12 metres per second and you're 108 metres above the ground. That's a long way. But what else might you want to find out? You might want to find the actual velocity of the object. In other words, the actual velocity that's travelling and the angle that it's coming in on. We've done vectors. We can do this. We've got this. So, I'm going to write up here t equals 4.7 seconds. Distance, horizontal, equals 56.4 metres. I'm going to get my trusty mask. I'm going to rub this out again. And we're going to figure out some stuff. Let's try and find out the final velocity of this thing. So, the velocity, vertical velocity, how might we find that out? It's vertical, so we're using this data. We're not using that data. That would be against the rules of physics. So, V equals, well, let's just say V equals U plus A times T. Vertical, vertical. I'm not going to say vertical time because time isn't a vector. So, VV equals 0 plus 9.81 times 4.7, which again, on a Monday, is 46.1 metres per second. So, what do we now know? We now know this object has a downwards speed of 46.1 metres per second, and it has a horizontal speed of 12 metres per second, which means